Hello, SC21. My name is Andy Hock. I'm the Vice President and Head of Product at Cerebras Systems, an AI computer systems company where we are on a mission to change the compute landscape by radically accelerating AI and HPC work by orders of magnitude for industry and scientific applications. At SC19, we introduced our innovative Wafer-Scale Engine and our first generation CS1 system. At SC20, we described the application of that system to HPC work such as computational fluid dynamics. Today, I will introduce our second generation wafer and system, additional applications to AI and HPC, and new technology innovations to enable extreme scale workloads, as well as our forthcoming lower level software development kit that will allow researchers and developers like you to bring completely new applications to life on our platform. In 2019, we introduced the first generation Wafer-Scale Engine, the biggest chip in the world by 56 times, to deliver cluster scale performance in a single chip. Earlier this year, in 2021, we announced our second generation Wafer-Scale Engine, specifications of which are shown here. We call this device the WSE2, with 2.6 trillion transistors on a single 8.5 by 8.5 inch unbroken piece of silicon and 850,000 AI optimized cores. The WSE2 delivers massive compute close to memory and ultra high speed communication, effectively a cluster worth of sparse linear algebra compute resources all on a single chip. Once we arrived on the wafer scale architecture as the right processing engine for deep learning and HPC, we had to completely rethink the system architecture required to power, cool, and deliver data to that high performance engine. For that, we are now shipping our Cerebras CS-2 system, which is built around the second generation Wafer-Scale Engine. This system has the same data center space and power footprint, as well as network connection as our first generation CS1, but with more than double the cores, memory, and fabric bandwidth inside. It deploys easily into standard data center infrastructure and delivers the compute performance of a cluster in a single system. Multiple CS2 systems can be clustered together to deliver supercomputer scale performance in just a few racks. For deep learning and AI, the CS2 includes a software stack that is designed to meet data scientists and ML researchers where they are today, using standard ML frameworks like TensorFlow and PyTorch to easily program our system. Our graph compiler automatically extracts and translates a user's training or inference program as written in their ML framework into an executable that's tuned to run on our Wafer-Scale Engine, giving our users access to this cluster scale compute device with the programming ease of a single node. The CS2 is built from the ground up to power both AI and HPC workloads, as well as a growing body of science and industry applications that leverage both. AI models, for example, are increasingly being used to inform or direct HPC simulations or real-world experiments so that researchers can arrive at insights sooner, using fewer total flops, and make more efficient use of best-of-breed hardware for their work in a heterogeneous cluster. In other cases, AI models are being used as surrogates for traditional physics-based HPC codes, delivering equivalent or better results with models informed by data that can operate at better compute efficiency. And throughout this landscape, there's a growing demand for extreme scale models that is simply not effectively addressed by traditional clusters of legacy general purpose processors. So by delivering a cluster worth of flexible sparse linear algebra compute balanced with high bandwidth memory and high bandwidth communication on wafer, our CS2 system is uniquely positioned to accelerate both pure AI workloads as well as pure traditional HPC workloads, as well as the set of work that exists at the convergence between AI and HPC. In the next few slides, I'll summarize a few recent applications of our system for supercomputer scale research in this space. First, at the Pittsburgh Supercomputing Center, we're proud to be a part of the innovative NSF-funded Neocortex AI supercomputer. There, a cluster of 2 CS systems serves as the foundation for a system designed to unlock interactive AI. That is, AI research that's accelerated in the pursuit of science, discovery, and societal good, where researchers can ask and answer questions with AI models at higher cadence to arrive at insights sooner. The Neocortex system itself, the design schematic shown at the right, connects to the Bridges 2 HPC system for data-centric HPC. We use an HPE Superdome Flex to store, quickly process, and stream input training data to the CS systems that are used as the engines for researchers' AI model training and inference. At PSC with Neocortex, I'm proud to say that we've completed a successful early user program with 17 AI research projects that use a wide variety of neural network architectures and data types in pursuit of problems ranging from clinical health imaging to physics-based atomic models for molecular modeling. Our work, though, at PSC is just beginning. I'm pleased to announce that Neocortex has just released a call for proposals for research and system time. Please visit the Neocortex website and reach out to the team there for more information. At Lawrence Livermore National Laboratory, we're working with partners at the intersection of AI and HPC. There, we have deployed a CS system and integrated that system into their world-class Lassen supercomputer. The researchers at the LLNL team are using these 2 systems together to accelerate fundamental research into nuclear fusion with so-called cognitive simulation. That is, physics-based HPC simulations that are informed by AI inference. By using the CS system to accelerate AI model inference of simulations powered by Lassen, the team there has been able to improve the overall computing efficiency of their work. This is a first-in-class example of system-level large-scale heterogeneity. That is, a heterogeneous AI plus HPC system. While traditional supercomputers often have the same node replicated over and over again, the CS system with Lassen provides a unique platform that is specifically tuned to run high-performance AI along HPC. Last but not least, we've continued our exciting partnership and work with the Department of Energy's National Energy Technology Laboratory, Nettle. Our initial work was originally published in Supercomputing 20, where the team there at Nettle is using partial differential equation powered HPC routines to simulate the fluid dynamics of combustion for energy generation. Using traditional systems that are often constrained by memory bandwidth and communication bandwidth between nodes, this kind of simulation computation is challenging and often time intensive. But by using the Cerebras system, our Wafer-Scale Engine, the team at Nettle was able to demonstrate performance 10,000 times faster than an NVIDIA V100 GPU and 200 times faster than the entire Joule 2.0 supercomputer, while saving orders of magnitude on power and cost. This remarkable performance gain is enabled by the massive memory bandwidth available to our compute, as well as our system's ability to execute sparse gem operations at full utilization. These architectural advantages are applicable not just to the stencil codes that power Nettle's work in computational fluid dynamics, but are applicable to a wide variety of important HPC work. Moreover, this faster than real-time simulation capability unlocks an entirely new set of capabilities and applications in this space. So we're really excited and look forward to many more opportunities like this one. But a common thread amongst these applications is an almost insatiable demand for more flexible, high-performance compute and growing model sizes. We see this in commercial deep learning and AI as well. For example, the plot here shows that over the past 3 years only, state-of-the-art natural language models for AI have increased in size by 3 orders of magnitude. BERT, for example, a state-of-the-art natural language processing model introduced in 2018, had hundreds of millions of parameters there at the bottom left of this plot. Fast forward in time, more recently, models such as GPT-3 have been trained with hundreds of billions of parameters. This is 1,000 times larger, 1,000x more compute in just 2 years. GPT-3 took 4 months to train on more than 1,000 GPUs. Existing infrastructure was fundamentally not built or optimized for this. Distributed programming for large-scale clusters is challenging, and brute force scaling for large workloads like this is not efficient. As we see here, distributed training performance, specifically in terms of speed up in time to accuracy as a function of growing cluster size. This is the metric that really matters for data science, research, and production, falls off rapidly as cluster size increases. That is, with larger and larger clusters of small traditional processors, the cost of communication grows, programming complexity increases significantly, the individual device utilization goes down, the total number of epochs to train goes up as learning efficiency becomes less efficient. At the bottom line, we need a new compute solution for large-scale deep learning and HPC. To those ends, at Cerebras, we've been working on this problem for some time, and earlier this year, we introduced a set of technological innovations that are designed to unlock extreme scale models, such as these. This new architecture is called weight streaming. The foundation of this approach is shown on the right, and the primary compute unit is our CS2 system. With 850,000 cores on a single chip, the CS2 is the large foundational building block on which all model layers can run without partitioning. Next, to handle models of extreme size, we disaggregate model memory from compute and add an external store to hold all the model parameters or weights. We call this technology memory X, pictured on the left side of the figure at the right of the slide. It's designed to support that disaggregation of model memory from compute and enable massive model sizes up to 120 trillion neural network weights. Truly incredible. That technology is optimized to intelligently stream the weights into the CS2 in a way that eliminates the impact of communication latency. Next, in order to scale beyond a single CS2 alone and completely independent of that memory, we introduced a smart interconnect technology called SwarmX that allows us to scale up the number of CS2 systems to deliver massive compute performance and reduce the training time to accuracy. It's also specifically designed to scale neural network training compute up to 192 CS2 systems with near linear performance scaling. Additionally, the flexibility and the native sparsity harvesting capability of the Wafer-Scale Engine at the heart of the CS2 systems unlocks not only larger models, but techniques that will allow the invention of smarter, more parameter-efficient models as well. This collection of technologies will allow us to for example, train GPT-3 in a day or train trillion parameter model over a long weekend. We can't wait to see what the SC community and beyond invent. And last, I'd like to announce, particularly to this community, that the advent and the forthcoming release of the Cerebras Software Development Kit, or SDK. At the end of this year, we'll be releasing the first version of this SDK, designed to allow developers to program at a more flexible, lower level directly for our architecture. As a part of this release, we'll be introducing a new domain-specific programming language based on C, using familiar parallel programming concepts. Primitives will include a library of neural network kernels and a library of BLAST kernels. Using this, users can program standalone applications, or they can combine new pieces with existing kernels in a modular fashion. The SDK includes a set of initial libraries that will be expanding throughout 2022 and leverages the same tools that Cerebras uses today internally for our own internal low-level development. So we're really excited to engage, particularly with the developer community at SC, to help unlock your creative ideas for Wafer-Scale and new applications, from computational fluid dynamics to molecular dynamics, simulations and signal processing. What else can be accelerated with 850,000 cores, all interconnected with massive memory and communication bandwidth? So I'd like to conclude by saying thank you for joining us today. We're really excited to work together to unlock the future of AI and HPC at ExtremeScale. If you're interested in learning more, our team has been working to enable the community and make CS2 systems available through multiple channels. You can purchase a CS2 system outright and deploy into your data center. We also offer mechanisms by which you can subscribe to CS2 systems hosted either at your facility or ours. And we recently announced a partnership with Wafer-Scale to make CS2 systems available through Cerebras Cloud, thereby making CS2 systems available to a much broader audience of users across industries who are working in a cloud environment. So please reach out to learn more. If you're interested, contact our ML enablement team online by visiting us at www.cerebras.com. ai.cerebras.net. Thanks once again and enjoy the conference.